Hello, everybody. Today, we're going to be going over Faraday's Law. This is part one of three of all of the cases of Faraday's Law. So, let's get into an introduction to what Faraday's Law is. Faraday's Law says that the integral of our induction field, E, is equal to the negative derivative of the integral of this of our magnetic field dot our little area right here that is changing. So as you can see here, we have these dot products. So we can just say that this is equal to b dot a, which will be negative d over dt integral of b dA, and then we just multiply by cosine theta. Because that's how we calculate the dot product. So this is going to be equal to what's called EMF. It stands for electric motor force, which is a highly misleading name because it is in fact not a force, but rather is measured in volts. Yes, but if you call it a voltage in front of your professor, he will hate you for the entire semester. So don't do that. Anyways, there are three ways to induce a magnetic field. We're going to be talking about one of them today. So, one way to induce a magnetic field is to change with time uniformly. Hold on. Forgot how to draw for a second. There we go. So imagine we have a magnetic field here, and it's going to change over time, i.e. get stronger or weaker over time. This is our first case where we have B of t is time dependent. Okay. Next case scenario is our area is time dependent. So our area is changing over time. Obviously, it's a little more uniform than this, but you get the idea. There we go. Okay, it looks uniform enough. It actually doesn't. Okay, there we go. Now it looks more uniform. Okay, so this is where the area, hold up, wrong color. This is where is time dependent. And then last example is our angle being time dependent, i.e. our angle is changing over time. So we have this right here, and let's say we just rotate it around this axis right here. Our rotating it around will induce an electric field. And we'll explore in part 3 what is ideal for increasing the flux and what is not ideal, and how to make calculations based on the angle. But today we're just going to focus on when our magnetic field changes over time. So let me extend the page. If we have a magnetic field that is, let's say, we have a magnetic field like this, where B of t is equal to B naught, so it's constant, and it's a uniform magnetic field. What would be the EMF of this magnetic field? So the EMF of this magnetic field, because here we have our, what's it called? Our derivative here is going to be constant because B naught is a constant. That means that we can say that the EMF is equal to 0. And the reason this is because in uniform space, we can simply write the EMF equal to the negative derivative of BA cosine theta. And our angle is constant, our area is constant, and our magnetic field is constant. So that means the derivative of a constant is always 0. So that means our EMF is 0 for this example. Now imagine we had an example like another, what's it called? Uniform magnetic field. If we had another uniform magnetic field, we have BT equals CT squared. So we're increasing over time. And let me actually label a height and a width for this. So our EMF, we have a uniform magnetic field, so we can get rid of the integral. And only for when our magnetic field does not change, or when only for when our magnetic field changes do we not need this integral, because if it's uniform, then we don't need the integral. Now, if it's not uniform, which we won't discuss in much detail, we will need the integral. So, at least not in today's episode, or like today's lesson. So the EMF is just going to equal negative derivative of CT squared, which is our field, times the area. The area is just height times width. And then times cosine. Our angle is going to be 0 because the, what's it called? The magnetic field is facing the same direction as the flux is going. So the angle is 0 between them. So cosine of 0 is just 1. And the derivative of CT squared is just 2CT. And HW can be moved out because it's constant. So we have that the EMF is equal to negative 2CT HW. And this would be your final answer. Now, a thing you can do is to find out what direction the current is moving, use Lenz's law. So we don't even really need to factor in the negative here because it doesn't really help us in finding the actual direction. What matters is that you put your thumb in the right place and that you get the right direction, whether it's counterclockwise or clockwise. So for this one, it'll be moving this way. It'll be moving clockwise, according to the right-hand rule. So let's move on to another example. So we have a circular magnetic field. Magnetic field here. Okay, well, it's good enough. And we're going to say that it's uniform and it has radius r. So what would be the EMF for this magnetic field? So this one is changing in time, but in this case it's a hoop, it's a circle. So our answer is going to look a little bit different. So our EMF is going to equal negative derivative of B. This is going to be B minus CT squared. So it looks like it's going to be decreasing. It's going to be a decreasing strength. And for this one, we'll have, what's it called? Oh, we'll have B minus CT squared times the area of this circle is just pi times r squared. And then times cosine of 0 because the flux is coming right at us. So the derivative of this will just be 0. Just cancel out. And the derivative of CT squared is just negative 2CT. So we're just going to have our negative pi, or we can move our negative pi r squared out because it's constant. And so we have a negative and a negative. That makes a positive. So in total, we have that the EMF for this one is pi r squared times 2 CT. And you can plug this into Ohm's law, and if you know the resistance, then you can find the current. But remember that EMF is not a voltage, but it is measured in volts, and it will work using Ohm's law or any other law that you want to use. Now, let's go over the last case scenario with this specific case where we have our changing magnetic field. So okay, let's make sure everything's the correct color. There we go. All right, we have a magnetic field here. And let's move it. And let's say we have flux coming this way. Or not, nope. We have flux coming this way out of it. And it has a radius r, which I think you'll be able to just deal with. And then it also has an angle. In this case, depending on what angle it is, it depends on what cosine of the angle is. So in this case, we're just going to worry about finding the formula for the EMF. So the EMF is simply going to be the negative derivative of, well, this field is represented by CT squared because our flux, our magnetic field is increasing over time. And since it's increasing over time, we'll have the negative derivative of CT squared, which is 2CT. And then we multiply by the area, which is pi r squared. and then times cosine of theta. We can't rule out cosine of theta and cancel out to be 1 because we don't actually know the angle. Because the angle, since the, what's it called? The magnetic field is facing this way, it's this angle between these two that theta is. And then cosine of that angle could be anything. So we're making a general thing here, but the angle is constant. So the angle is always the same. As you can see, it's relatively the same. So our EMF is going to equal negative 2 pi r squared CT cosine theta. Because cosine can go out, pi r squared can go out, and then we just are left with negative pi r squared CT times cosine theta after we take the derivative. So here is the angled version of what we just did. Anyway, I hope you like this video. Part 2 coming out tomorrow, and I will see you all later. Goodbye.